There we go. And okay, let me just continue from where I left off there. Sorry about that. The whole point of what I was saying there is if we're building things up using low-pass filters as our underlying synapse, there was a bunch of weird math that I just showed, right? And that if you want to work with different sorts of synapses, then you can sort of go through that same math, but with a different synapse model. But the punchline is going to be that if I have any sort of differential equation that I would really like to implement in any of these sorts of forms, what I can do is just implement that same dynamics multiplied by tau plus a feedback term. Okay, that's the take my dynamics of what I want, multiply it by tau, and add a feedback term just for that recurrent connection. Multiply the other input by tau, and I can build up whatever I want. Another way of phrasing this is the synapse is giving some sort of low-level dynamics to my system, and what I can do is I can exploit that low-level dynamics to implement other dynamics. I'm not limited by whatever dynamics my low-level synapses are. I can do a combination of this function approximation trick and my low-level dynamics to go implement other dynamics. That's new, that's weird. What's some examples of what I can do with that? Well, let's go back to this low-pass filter example, because this is at least something where we can sort of see, hey, this might be a useful computation that a system might need to do. Okay, engineers use low-pass filters all the time. So say I've got some sort of noisy input, and I just want to know, okay, just give me a smoothed version of that input. Okay, but if I implement this with just the synapse, right, because the synapse model, this was supposed to be about, oh, there's neurotransmitter being released, it's being reabsorbed over time, and different neurotransmitters have different time constants. And that's going to mean that there's some limited range of low-pass filters that just simply saying, oh, I'll just use a different synapse and that'll give me a different low-pass filter. That's going to limit me about what range of low-pass filters I can do. What if I want, as an engineer, to say, oh, I'd really like a biological system that has a low-pass filter with a time constant of 1 second. But I don't have any neurotransmitters that have a time constant of 1 second. What can I do? Well, this is saying that I can use whatever neurotransmitters I happen to have and go and implement something else. So, how do I build that up? First of all, I need a differential equation to describe what I want to build. Okay. And now we're now getting into a sort of a very explicit engineering sort of approach of, look, this is what I want to build. I'm going to write out the math. The math is going to tell me what groups of neurons I need and how to connect them. Okay. So, I've got some input U, and I've got some value X, and I would really like X to be a smoothed version of U over some time window. Okay. And I go and ask my nearest engineering friend, what's the differential equation for a low-pass filter? And they tell me this. Okay, there is some time constant of the low-pass filter, and that's the differential equation for it. And we say, okay, fine. This is what I would like, how I would like my system to behave. What does that mean? Well, part of this differential equation is about my input. Right? U is my input. It's being scaled by tau desired. There was a bunch of weird math, but the heuristic that all I need to remember is take the part that's about my input, multiply it by the tau of whatever my synapse model is. Okay? I'm normally writing this as just tau in all the previous pages, but because now I have this differential equation where I have a tau desired, So just for sort of clarity, I'm writing just tau of the synapse and tau of whatever my desired low-pass filter is. Okay, so I just take the part of the equation that's about that, multiply it, fine. And this is saying this is the function I want to approximate on my input. Okay. For the recurrent connection, the function that I want to approximate from, there's going to be some neural population representing U and another neural population representing X. So this recurrent thing, that's going to be a connection from the neural population representing X back to itself. And all I do is I take, all right, part of this equation that's about X, negative X over tau desired. I multiply it by the tau of the synapse, and I add X. And maybe I do some rearranging if I feel like it. Okay, those are the same. That's telling me what function I should approximate on my recurrent connection. Does that work? Well, let's go back here and find out. Okay. Let's go copy this code, put it over here. All right. Let's go build something up. Fine. Yeah, let's just do this from scratch, sure. Let's have an ensemble. That's my population representing U. Here's my population representing X. I guess I'm going to need some sort of stimulus so that I can feed that in. So the stimulus for U is going to be, stimulus over time. What am I doing? Return 1 if t is less than or greater than 0.5, else 0. So again, we're just going to do a sudden jump as my input. I'm going to have some node. And we're going to make a connection. U to U. Alright, that's going to be feeding in this function. And we'll be even a little bit more specific and to say, hey, don't even bother putting a synapse on that. Okay, so that's feeding in my stimulus to that first population. Fine. Now I want to do that weird math in order to make X be some low-pass filter. All right, let's define some variables. So let's say I've got a synapse of 10 milliseconds, but my desired low-pass filter is 1 millisecond. Okay. My feed-forward function, that's a function of U. What is it? Tau synapse divided by tau desired times U. Alright, that's a function. I'm going to make a connection from U to X where the synapse is the tau of the synapse. Make sense? That's all using the things that we've seen so far today. And I'm going to have the recurrent function. What's that function? Well, that's going to be 1 minus synapse over desired. There, and we're going to make a connection from X to X where the synapse is the tau of the synapse. All right, is that going to do what we want? Well, let's probe on X, and we should probably probe our stimulus. Oh, and that probe on X, just because we're going to be plotting it, I really should put in some sort of small synapse on there, just so that we can actually plot its value. Now we make our simulator. With the simulator, we say sim.run for 1 second. Oops, and I've done something wrong. What did I do wrong? Oops, it's not probable on node. What? What did I do wrong? Oh, it's not called stim view. There we are. I just connected it to totally the wrong thing. Good. Now, range. So what's that stimulus? Okay, there's our stimulus. X. We did something wrong here. What did I do wrong? I forgot to add X. What else did I do wrong? Shoot, I've done something wrong. What did I do wrong? Just one. Did I do my math wrong? Oh, whoops, no. I did do that plus X, that's fine. X to X. Oh, this is embarrassing. What am I doing badly? Mute X. Oh, I'm an idiot. I didn't actually tell it to use these functions. There we are. Desired. And there's a stimulus. Let's run it for a little bit longer. All right. So we can have differential equations doing things. Let's go give it a few more neurons, just because I'm finding the accuracy isn't quite what I want. All right. Now, is it doing what we want is sort of the key question here. So first of all, now since I've got these things as variables, I can go ahead and check it. So what I'm saying here is I have a 10 millisecond synapse, and we'll go back to 1. Okay. And if I do the 10 millisecond synapse, that's what a 10 millisecond synapse does. If I would like 100 millisecond synapse, okay, this is what an ideal 100 millisecond synapse looks like. Okay, so this is saying, sorry, let me take a step back there. What I'm doing is I'm saying, all right, I've got two different things I can play around with here. What synapse do I actually have? What synapse do I want to have? If I set these two to the same thing, take a look at what's happening to the math here. All right, if I set these two to the same thing, well, that means my feed-forward connection is 0.1 divided by 0.1. That's 1. So my feed-forward connection is just the identity function. And my recurrent connection is 1 minus 0.1 divided by 0.1. That's 0. So that's the 0 function. So that means my recurrent connection is just going to be all zeros. All those weights are just going to be 0, because that's the best way of approximating 0. So if I set these two to the same thing, then that's, it's sort of a nice check. That's just simply saying, look, if my dynamics are already what I want, then I don't need this recurrent connection at all. Okay, so that's one way of saying what we're doing there. And I'm just using that as a way of plotting, okay, this is what a 0.1 millisecond low-pass filter looks like. Okay, I'm changing my input, and I get that. Now, if I do something like I say, hey, all right, what if my actual synapses are only 50 or only 10 milliseconds, but I want the system as a whole to behave as if it has this long 100 millisecond filter, then I can get a bunch of 10 millisecond things to behave like a 100 millisecond thing. Okay. And again, the intrinsic dynamics that I'm giving it there, so if I wasn't doing any of this weird tricks, so we've got some sort of recurrent function being computed here. If I wasn't doing any of those weird tricks, if I didn't have that recurrent connection, the behavior would have looked like this. This is what the neurons, or this is what the synapses sort of inherently are doing. This is the dynamics of just the synapses. But then I can combine those using, I can find a recurrent set of weights that will use that low-level, very fast dynamics in order to compute something much longer dynamics. Okay. So even though the neurons themselves, the individual synapses have a very short time constant, the system as a whole is smoothing data over a much longer period of time. Okay. So it has some sort of memory. That's another way we could think of that. Interestingly, we can go the other way around. Let's say I have 100 millisecond synapses, right? So again, so this is what the dynamics is actually doing. But then let's say, all right, I've got all these neurons, these synapses that are behaving very, very slowly. They have this, they're causing a very, very slow response. I change my input pretty quickly here. It takes a while for the neurons to change their activity in response. But I could say, all right, well, what if I want a 10 millisecond response? So I want to use a bunch of really, really slow synapses to do something fast. That seems a little weird. Can we do that? I mean, there's nothing in the math that says we can't. Is something going to break? Nope. I can have a whole bunch of very, very slow synapses work together to pass information quickly. Okay? This might be another reason why biology might be doing a lot of recurrent connections, is that it is possible to compensate for the fact that synapses are can be very slow to pass information more quickly by adding in recurrent connections that do what you want. Okay. So these are just examples of building up various different, these are different types of differential equations that maybe I might want as an engineer. Please pass me information from one place to another. I know my synapses dynamics are going to do something. I want to exploit the synaptic dynamics to do something else. Cool. So we can do low-pass filters. What else can we do? So certainly there's a whole family of different, there's tons and tons and tons of differential equations out there. And so yes, you can do all of them. The limitation, of course, is going to be how well can you approximate those functions. There's one particular differential equation that is going to tend to be really useful, or that we find tends to come up a lot when we're building models. And that's the differential equation of an integrator. Okay. So if you do that same trick that we just described, all right, you say, all right, give me the differential equation for an integrator. All right. Cool, now we can get a system where if we pass in sort of a pulse like that, now the internal representation is going to go up, and then when this pulse comes down, it's going to stay where it is. Okay. That's going to be kind of cool, because that's going to be something that is going to remember information over time, because, hey, my input is now 0, but my value is actually, whatever value was at when we pulled my input down to 0, we're going to stay at that value. If I compute the integral of a sine wave, I get a cosine. All these sorts of standard tricks. So computing the integral is something that shows up in math a lot, so unsurprisingly when we try to build large complicated systems, we might also want to be able to compute an integral. It's kind of useful. This exact same approach works fine for it. This is also sort of the point where, depending on how people want to think about differential equations, there's going to be a bunch of different ways of thinking about what this system is doing. One common way of thinking about differential equations is to start thinking about these phase portraits. And so what? This is either a refresher for some people, or this is totally new for other people. What we're plotting here is, on the x-axis is what the value in the integrator is. Okay, so I don't know. So I've got some value in my population x, and let's say, I don't know, maybe it's 1. Okay, and then my input that I'm giving to the system is on this axis, and let's say my input is 0. All right, at this, let's say my input is -1, and then what that's saying is, and the reason that there's arrows here is that if my current value is 1 and my input is -1, well, that means that I should decrease my value. Okay, and that's what these arrows are saying. And the farther down my input is, the faster I'm going to decrease these values. If my input is 0, then I'm going to stay wherever I am. Okay. So this is sort of a weird way of thinking about what of what an integrator is. You know, it's a value where, or it's a system where if my input is 0, then I stay with whatever value I'm on. That's this blue line is saying stay still. If my input is positive, then follow the arrows. So it's saying, okay, go to the right, go to the right, go to the right, go to the right. If my input is negative, then it says go to the left, go to the left, go to the left, go to the left. I'm going to keep on going. So that would be the way of understanding what a ideal integrator would do. But when we approximate an integrator with neurons, we're not getting exactly this behavior, because we need to pick some range of x that we're approximating over. Okay. So in order to sort of understand, well, what's happening in a neural integrator, we can generate these same sorts of plots, but for whatever the neuron model actually went ahead and approximated. And if we do that, we get this thing on here on the right. Inside the range that we optimize it for, it's pretty much the same as the integrator. Right? I've got some sort of values that I'm kind of stable for. Okay. If I'm positive, I'm going to go to the right. If I'm negative, I'm going to go to the left. But if I start pushing and putting in values that are too large, eventually I'm going to stop changing. Right? This is the advantage of plotting things this way. I can just sort of look at, okay, if I hit the blue line, I know I'm just going to stop. Right? And I know that if I go too high, if x manages to be too high, no matter what the heck is going on over here, no matter what my input is, I'm still going to get pulled back. Okay. Whereas with the ideal integrator, it'll just keep on going forever. So this is sort of a little bit of a, potentially useful for some people, sort of a shorthand of understanding how this system is actually going to behave. There's also this aspect that this perfectly flat line, when the input is 0, it's not going to be perfect. Right? And what this is going to end up indicating is there's going to be some values where even though my input is 0, I'm going to drift up or drift down a little bit. Interestingly, this sort of thing does seem to be what we're going to get in real biological systems, that it's not perfectly able to store any particular value. It'll sort of drift towards particular ones. All right, I'm mostly just pointing out there that yes, you can analyze these sorts of things in terms of these phase portraits if that's what people are used to for these sorts of differential equations. May or may not be useful for depending on what your background is and what it is that you want to do. There's lots of other differential equations out there. There's oscillators. Fine, you can go ahead and build oscillators. They actually, since a lot of oscillators tend to be pretty linear, it turns out that you get a pretty good match between the ideal and what ends up happening with neurons. You can implement Lorenz attractors. Fine, you can do chaotic systems. It's a nasty differential equation, but it's not horribly nasty. It only has, it's got a couple crosswise terms or quadratic terms, but it's not horrible. So we can go ahead and implement differential equations that are chaotic, no problem. Do other weird sorts of math or make heart shapes. And one thing I definitely do want to point out is this can be some of the very first things where we're actually trying to take the techniques that we're sort of describing here and applying them to actual biological systems. Because there was an example that was briefly mentioned a while ago about horizontal eye control. So you have muscles that are controlling the horizontal position of your eye. It turns out that if you take a look at the signal that's being sent into those muscles, it's a velocity signal. Right? The velocity is being fed in, so there's an input that is pretty much always 0 when your eyes aren't moving, and then you get an input that sort of shoots up when the eye is supposed to move, and then goes back to 0 again. And if you treat this as an integration, where the integral of velocity is going to be position, and you go ahead and build the model using exactly the techniques that we just described, you get a system that gets about the same level of accuracy as what you see in biological systems. So for instance, in goldfish, there are 40 neurons involved in this process. In humans, there's something like 400. And so you can look at the levels of accuracy that come out of those two systems, and you say, okay, how accurate is it? It also turns out that it's not exactly the mathematical equation for an integrator that best matches the behavior. When you go ahead and try these sorts of tasks in real animals, you get them to move the eye to a particular location, there is drift back to a center location. Okay? You can express that somewhat like a low-pass filter. There's a little bit more of this more details of this in the actual, in the notes for this. So you can write that math. It's very similar to the math of the low-pass filter. And we can go ahead and build that model. And now you get these systems that do exactly what you see in the real biological system is you go ahead and move the eye, you get drift back towards the center location, and that drift eventually stops at some point. So you can go ahead and compare that to biological systems and build up models of that. Importantly, it's tricky and it's very difficult to build those sorts of models, sorts of recurrent models, using the traditional sorts of deep network techniques of doing backpropagation. The whole point of what we've just shown here is this is a really weird way of generating the connection weights for recurrent connections. This is I don't know, I want to say more flexible. This is a very different approach than what happens when you do with backpropagation training. So this can build these sorts of models much more efficiently, more accurately than what people tend to find if you try to do that with backprop. The problem, of course, with trying to do these sorts of, here's some differential equation that I would like to train up with backprop, it turns out that you just need tons and tons and tons of training in order to do something like that. Whereas taking these equations, breaking it down into the two functions that I would like to break this down into, and then just training and feed-forward networks for doing each of these two, or not even training, but solving for the feed-forward networks that do these two parts, and then combining them back together to give you this, ends up being a very general method for building these networks using much less training data and much better sort of what classes of things you can actually do this way. All right, that is dynamics. That's hopefully a little bit weird. So again, conceptually, there's nothing new in terms of how we're making these connection weights. Right? We're making the same connection weights the same way we do for the feed forward. We're just implementing them recurrently. But this whole thing of, all right, now I can implement differential equations, that becomes a really hard thing for people to learn how to do. It becomes really hard to figure out what the consequences of that is. And I find a lot of what my work now is when I have theories about how cognition works, the tricky part is how do I break that down into variables, feed-forward functions, and differential equations. Okay. I'm not used to thinking in terms of differential equations. And certainly psychologists and people coming up with various different theories about how the brain works are not used to thinking in terms of differential equations. But what this math that we sort of went through in these lectures indicates is that differential equations are the natural way of expressing this is what recurrent neural networks are good at. So hopefully we can sort of we'll sort of try to do more examples of these things and try to see what are different possibilities of things that you can build in order to take sort of existing behavior and converting them into this sort of and converting into the form of these sorts of brains. We'll be doing a little bit more of that in the next lectures. And then the other big part is going to be sort of like analyzing, well, what sorts of functions are we allowed to do in here? And so that's because that's also going to tell us what sorts of differential equations are we allowed to do. Cool. Thank you very much, and we will see you next time.